Okay, so now I can feel the excitement in the air. We're starting our second part of the course, which is all about snakes. Neat. Okay, so integral calculus. But I'm actually going to cheat you a bit, because we're going to start by discussing snakes, but they're going to be what are called indefinite integrals. And in fact, those are really related to derivatives. They really belong in the previous part of the course. And how they relate to the other forms of snakes that we're going to see, which are really the integral calculus, that's only going to show up next week. So let's start by some definitions. Definition. Oh, and one more important thing. We're going to use little f and big F today. And it's very important that they look differently in your notebook. So make sure you write big F, big and block stylish, and little f, make it small and you know. Okay, so a function, big F of x, is called an antiderivative of little f on I. I is some interval. So I stands for interval. If, this is going to shock you. Sit down. Hang on. If, for any x in I, the derivative of big F is little f. Right. Okay, so does this definition make sense? Okay, I'm doing the opposite thing of taking a derivative. I'm looking for the function, so somebody gives me little f, I want to find big F. Okay, so big F is an antiderivative of little f. Theorem. I is some interval. I said that. Okay. So theorem, the collection of antiderivatives of some given function little f on some interval I is of the form. So before I write of what form, note that I wrote the collection of antiderivatives. So implicitly I'm saying here, when you take a function and you want to find its derivative, there's only one, right? Taking a derivative of a function is an operation that results in one answer. When you take a function and ask what functions is it a derivative of, there can be more than one answer. There can be more than one correct answer. And so that's why I call it a collection. But in fact, it's not just a bunch of random functions. They're a family. They're closely related. There's daddy function, mom. No. They're a family, and they're of the form. Take one of them, call it big F. All the rest are of the form f of x plus c. So this c is any constant. So c belongs to R. So let's just wave our hands a bit and then we'll write a formal proof. What is the statement here? The statement is, take a function. Think of a function. Can you imagine a function? If it has a derivative, little f, any function which is exactly the same but moved up or down, okay? So if you take two functions which look exactly the same, but one is the other plus 5, they would have the same derivative. Do you agree? Do you see that? Everybody? You're missing the intuition back there. Two functions that look the same but have a difference of a constant have the same derivative. Do you agree? So saying that if f is an antiderivative, then adding any constant would give you still an antiderivative, that's kind of convincing because of this argument, right? Why are there no others? Okay, so for that we need to kind of write the formal proof. There are infinitely many, exactly. So proof of this theorem, proof, if f prime equals g prime, if two functions have the same derivative, then f is, or I wrote it g, then g is f plus some constant. So if two functions have the same derivative, they're actually the same up to a constant, up to an additive constant, because, let's argue this, define h to be g minus f, the difference function. What is h prime? What is h prime? It's g prime minus f prime, right? But g prime and f prime are the same, so this is 0. Do you agree? But if h prime is 0, what does that mean? H is just some constant. And therefore, g minus f is a constant function, and therefore g is f plus some constant. So two functions share the same derivative if and only if they differ by a constant. Okay? So that's that previous statement. And now there's the notation. Notation. Snake. And this is the weirdest notation one can think of. I mean, if I would have to come up with a notation for the antiderivative, well, if the notation for the derivative is a little prime thingy on the top right, then a reasonable notation, I think, for the antiderivative would be maybe a prime on the other side, or maybe a little prime down here, or maybe a squiggly tilde up here. But why on earth would you write this? This seems way too sophisticated, and so the answer is, the reason for that thing is because of a different type of integral, okay? And the relation between this and the different type of integral, which we will discuss next week, is very deep. It's not trivial. It's called the fundamental theorem of calculus. Okay? So for now, it's just notation. Don't ask me why. Why? Next week. Okay? So this is notation. This thing denotes the family, the collection of antiderivatives of f. So this is not a specific function, it's a family of functions, all differing by a constant, and they're all antiderivatives of f. They all have the property that their derivative is precisely the little f living inside the snake. Okay? And it's called, this is called the indefinite integral of f. Okay? Definite integrals and their relation to this next week. Example. Everything here is notation. The notation is made up of two things, this dx thing and the snake. And that's it. That's all we're going to say about it now. Okay? We'll say about it more. Okay, so what's the indefinite integral of sine x dx? How do I do this? Well, the first examples, this is example 1, are just going to be what are sometimes called immediate integrals. The way to solve them is just by knowing derivatives. So sine is a derivative of cosine. Not exactly. The derivative of cosine is minus sine, so we need to put a minus here. Okay, and we need to add plus c to indicate that it's not just this function, but this function plus any constant. So if you take minus cosine of x plus 5, its derivative is going to be sine, because the derivative of 5 is 0. Do you agree? Okay, so you have to remember this plus c business. I need a volunteer, boy or girl. So I like it. Some people raise their hands, and other people do to the person sitting next to them. So we'll not force anybody. So who volunteered? Okay, you're our volunteer. Your name is going to be, as a volunteer, it's going to be Plussy. 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 But what it means is you're going to remind us to write, you're going to have to shout, plus C, whenever. No, you spell it like this. Okay? Okay, plus C, just don't forget your role. Example number 2. We'll discuss later how important this plus C can be. It's not just remembering to put it or else you lose a point on the exam. It actually has an important role, and we'll see examples. Okay, so another example, suppose we want the integral of x dx. So what's the integral of x? Well, x is the derivative of x squared. But wait, that's not accurate, because the derivative of x squared is 2x. We don't want 2x, we just want x, so we multiply by 1/2. Thank you. Clear? So all these are called immediate integrals. Immediate integrals. Okay, remark. No. You're going to be fired. You can only say your name when it's relevant. Okay? In fact, I've been doing this plus C joke for quite a few times. That never happened to me before. That somebody just started getting carried away. Okay. Remark. Not every f has an antiderivative. Not every function is a derivative of something. Can you argue this? Can you tell me why is this true? Or give me an example of a function that's not a derivative of something. Easy examples. Don't do anything. Absolute value of x. So absolute value of x is a derivative of something. Okay? And I know that because we're going to have a theorem later on that every continuous function has an antiderivative. An absolute value of x is continuous. Okay?
It doesn't have a derivative.
But we're not asking if it has a derivative. We're asking, is it a derivative of something? Does it have an antiderivative? Okay? You're going to say dirich le whenever we need an example of a function. Why? Okay. No, we don't care about it being differentiable. We're caring, why is it not a derivative of something? Okay, I want a simple argument, a very simple argument. So the answer is something we said. We said that derivatives don't have to be continuous. Remember we said that? Derivatives can have points of discontinuity, but only of a specific kind. Essential discontinuities. Remember we said that? So if you take a function with a jump discontinuity, for example, it's not going to be a derivative of something. It cannot be a derivative. So here's an example, and we can actually argue it manually. So suppose you take the function, let's say that it's 0. I'm drawing 0 a bit up so you can see it and it doesn't coincide with the axis, and 1. Okay, so it's 0 on the negative axis and 1 on the positive. So this is going to be little f. I want to argue that this cannot be a derivative of anything on R, on the real line. Okay? So suppose we were to, let's look for capital F. Let's look for a function for which this is a derivative. So a candidate would have to satisfy that whenever x is positive, it has to be x, because the derivative of x is 1. Do you agree? Or x plus c. That would still work. Whenever x is negative, the derivative has to be 0. So it has to be constant. It has to look something like this. So this is a candidate for the antiderivative, for big F. But this candidate is not an antiderivative because it has a cusp at 0. It's not differentiable at 0. Do you agree? Clear? So this function does not have an antiderivative. It's not the derivative of any function. It's the derivative of a function if you restrict only to positive numbers. It's the derivative if you restrict only to negative numbers, but not if you want to have an interval which includes 0. Okay? Clear? And a more general argument, so this is a candidate for f, but, oops, not differentiable at x equals 0. So it's not an antiderivative. So this little f does not have an antiderivative. And a more general argument would be any function which has an antiderivative, meaning it is a derivative of something, has to satisfy Darboux theorem, has to have this mean value property, this intermediate value property, can only have essential discontinuities, and cannot have jumps or removable discontinuities. Okay? So that's this statement. Some rules for differentiation. Some rules. Some trivial rules to start with. We'll get to more sophisticated ones as we progress. I'm going to leave the snake. I like him. Okay, so rules. Rules is another way of saying this. These are theorems. You have to prove them. The proofs are actually easy, but we're going to skip them. So 1, if you want the integral of some constant times f of x, you can pull the constant out. This is for any a in R. No, we're not calculating here anything. Okay, and the second is that the integral of f plus g, let me not write the x dx just for simplicity, just like we didn't do it with derivatives. Okay, so this is, it's not really appropriate to write it like this, but just for simplicity. So this is the same as the integral of f plus the integral of g. So these rules are called, together, they're called, what? Well, you could call them integral arithmetics, but the actual name is linearity. Okay, this means that taking the antiderivative is a linear operation. It respects constant multiplying by constants, or by scalars, and it respects addition. When you learn algebra, you'll learn about linear spaces, or vector spaces, and linear operators. Okay, and then you will remember this statement. Okay? Don't worry about it if it's confusing. Let's do more examples. So more examples. Example 3. Suppose we want to do the integral of 1 over 1 plus x squared. What's the antiderivative? Right. You should recognize this as arctan x. Okay? Another example. What about the integral of root of 1 minus x squared? Note that I did here something that is very common. When the numerator of a fraction is just 1, people often write the dx up on top here, as if it were. So this is just standard way of writing. Okay, right. This is arc sine x. And these are all immediate. The only way I know how to solve them is I'm not performing any fancy operations here or using any theorems. I just know these. Okay, I know that the derivative of arc sine is this. I know that the derivative of arctan is this. You have to know that, of course, and then you know how to solve these. Okay? More examples. Don't worry, not all our examples today are going to be so elementary, but it's important to mention those at first. Let's do one more and then do some trickier ones. So example 5, e to the x. So what's the antiderivative? E to the x. Okay. What if I had e to the minus x, for example? Right. Then I would write here e to the minus x, but the derivative of this is e to the minus x times minus 1, the inner derivative. I don't want that minus 1, so I put a minus here. Clear? So that's always kind of the way I usually do it. I first write the obvious candidate. I know I'm going to have to fix it. Then I take the derivative and see what I have to fix. Okay? Okay. Here's another example. What's the antiderivative of 1 over x? Note that this is not defined for x's which are equal 0, so I'm going to restrict and say that x is not 0. Right, so you're going to write ln of x plus c, but wait. ln of x is only defined for x greater than 0, right? So this cannot be an antiderivative of 1 over x on negative x's. Right. So the answer is it's ln of the absolute value of x plus c. And the reason for that is, so let's explain this, because ln of absolute value of x is ln of x when x is positive, and ln of minus x when x is negative. Do you agree that this is the same thing? That's what ln of absolute value of x means. Except I wrote positive in both cases, which is ridiculous. Do you agree? Everybody? Okay. So, what is the derivative of ln of absolute value of x? When x is positive, it's the derivative of this, 1 over x. Do you agree? When x is negative, it's the derivative of this, which is what? It's 1 over minus x times the inner derivative, minus 1. Do you agree? So what we got is that it's 1 over x, whether x is negative or positive, as long as x is not 0. So the derivative of ln of absolute value of x is 1 over x. So the antiderivative of 1 over x is ln of absolute value of x for all x's except x equals 0. Good? Okay, this is a very important example as well. Okay, more examples. So far all of them are kind of considered immediate integrals. Ones that you really don't have to do much other than know your derivatives. Okay. So sometimes things are not completely immediate, but are almost immediate, such as in this example. So x to the 4th divided by 1 plus x squared. So I doubt that anybody can, without writing anything or solving this in any way, just guess the antiderivative of this thing. It's not immediate. It's not one of the standard functions for which we know derivatives, right? But all we need to do here is some very standard algebraic manipulations. So what I'm going to do is a standard manipulation like that. I'm going to subtract 1 and add 1. I don't need to. Oh well, it doesn't matter. So this is a standard thing to do. And the reason for doing that is that x to the power 4 minus 1, I can now rewrite as x squared minus 1 times x squared plus 1. Do you agree? And now, for this part, they cancel. So what I get is the integral of x squared minus 1 dx plus the integral of 1 over 1 plus x squared dx. And I can do this step because of the linearity. I broke it up into a sum of two integrals. Do you agree? And now they're really immediate. So x squared is the derivative of what? Of x cubed. But not exactly, because the derivative of x cubed is 3x squared. I don't want the 3, so I multiply by 1/3. Minus 1 is just the derivative of x, plus arctan of x plus c. And this is the antiderivative of this. Do you agree? So calculating antiderivatives, there could be a bit more to it than just knowing your derivatives. And we're going to see many methods. Okay? But one thing is important to remember. Once you got to the end, and the end is when there's no more snakes left, okay, you can always check if what you did is correct or not. How do you check? Take the derivative. If what you did is correct, you should get this for the derivative. Right? So, always verify by taking the derivative. Sorry? Always
Verified by, no.
Oh. Sorry. Always verify by taking the derivative. Okay, sorry. Okay. So what's the derivative here? It's what? It's it's x squared minus 1 plus 1 over 1 plus x squared, and then you do a common denominator and you get this, right? Okay? Okay, so that's example number 7. Example number 8 is again one where, let's start a new board. Example number 8 is again one where we need to do some manipulations. This time the manipulations are going to be trig-ish. We're going to use some trigonometry moves. So 8, suppose we want to find the antiderivative of tan x. Again, this is not an immediate one. Okay? We know the derivative of tan x, but we don't know, at least I don't know by heart, well I do know because I know this too well, but usually we don't know a function whose derivative is tangents, right? It's not one of those on the list. So how do we do this? So for example, we can write tan as sine of x over cosine of x, right? And then, note the following. What we have here is a function in the denominator whose derivative is in the numerator. Do you see that? Up to plus or minus. Do you see that? So my claim is that the antiderivative is ln of absolute value of the denominator. Well, we'll fix it. We'll fix it. Why is this true? Because what's the derivative of ln of absolute value of something? As we argued before, it's 1 over the something, 1 over cosine, times the inner derivative. The inner derivative is sine. Well, we need a minus here because the inner derivative is minus sine. Now, before you get to ask your question, plus y? Whoa. Okay, now you can ask your question. Okay, so what just happened here is part of a more general statement. So let's write it in general. In general, if you have the integral of some function living in the denominator of a fraction, and its derivative living on top, then the antiderivative is going to be ln of absolute value of the bottom. Because the derivative of this is 1 over f times f prime. Clear?
Where did the minus came in that case?
Here, because the inner derivative of cosine is not just sine, it's minus sine. So compensating for that, we put a minus, and then we just get sine. Okay, so you can remember this as a formula if you really want to. It's just a standard kind of observation. Okay? Okay, so maybe we'll... let's take our break now. Today we have 3 hours, so we have 2 breaks. So let's take another break now, and we'll continue this after the break.